This resource is the seventh in a series on derivatives. We will explain the concept behind derivatives and formally define them. We will discover how to find the derivatives of various forms of functions, including polynomials and trigonometric functions. We will consider how to differentiate products, quotients, and composition of functions. We will also consider applications for derivatives and how they relate to real-world situations. Think back to when we first defined the derivative. We determined that the derivative is the instantaneous rate of change for a function. But what happens if that rate of change is zero? This means that a line tangent to our graph is perfectly horizontal. This only happens when the graph has a local maximum or minimum, that the graph is at a peak or a trough. So by identifying where the derivative is zero, we find the turning points of the graph. Now to blow the mind. What happens if we take the derivative of a derivative? We can surely do this. For notation, we have d squared f with respect to x squared, or f double prime of x. But why would we ever want to do this? What information does this second derivative give us? Actually, quite a bit. Suppose we found values where the derivative is zero. We can check that value in the function defined by the second derivative to determine if that amount is positive or negative. If the second derivative is negative, then the graph at that point is concave up, which means that the turning point is a local minimum. If the second derivative is positive, the graph is concave down, and the graph has a local maximum at that point. But how exactly does this help us? Remember, when we take the derivative of a polynomial, the degree gets lowered by 1. This makes the derivative an easier equation to have to solve. Because of that, sketching the graph will be a much easier task if we just go through the following steps. First, find the y-intercept of the graph by plugging in 0 for x. Then, calculate the derivative. Set that derivative equal to 0, and solve. For each of these x values that are local maximums and minimums for the graph, find the corresponding y value. Next, we will calculate the second derivative. Plug in the x values and determine if the graph is concave up or down at that point. Let's see an example. Suppose we want to sketch a graph of the function f of x equal to x cubed minus 6x squared plus 9x plus 5. First, we can find the y-intercept. When we plug in 0 for x, 0 to any power is still 0. So all that we are left with is a y-intercept of 5. To find the derivative, multiply each term by the original power and subtract 1 from the exponent. Also recall that the derivative of any constant value is 0. So we have 3 multiplied by x raised to the power 3 minus 1, minus 6 multiplied by 2, x raised to the power 2 minus 1, plus 9x to the 1 minus 1 power, plus 0. After simplifying, f prime of x equals 3x squared minus 12x plus 9. We set 3x squared minus 12x plus 9 equal to 0. To begin solving, we can factor out 3 and be left with x squared minus 4x plus 3 equal to 0. This is nicely factorable, so we have the quantity x minus 3 multiplied by the quantity x minus 1 equal to 0. We split the factors into separate equations. Solving each of these individual equations, we have x equal to 3 or 1. To create our graph, we need the corresponding y values for the x values we just found. To do so, we plug each value into the original function, f of x equal to x cubed minus 6x squared plus 9x plus 5. Plugging in and solving, we find that f of 3 equals 5. Substituting 1 for x, we find f of 1 equal to 9. Next, we will find the second derivative. We had the derivative equal to 3x squared minus 12x plus 9. When we take the derivative of that function, we are left with 6x minus 12. Our last step before actually graphing is to determine the concavity at each of the x values that result in local extrema. When we plug 3 into the second derivative function, we get a value of positive 9. This means that the graph is concave up at 3, and 3 is a local minimum. Plugging 1 into the second derivative function, we get negative 6. The graph at 1 will be concave down, resulting in 1 being a local maximum. Now that we have done all the background work, let's sketch our graph. We plot the points for the y-intercept of 5 and the local extremes at 1, 9, and 3, 5. Connect the points with the appropriate concavity, and we have a perfectly serviceable sketch of f of x equal to x cubed minus 6x squared plus 9x plus 5.